just share it. Okay. Hello? Yeah. Is this audible? Okay. So yeah, so we won't keep you for a long time here. So first start with the introduction. My name is Veena. I currently work at Uber. Before that, I was at Cloudera for a brief time, where I picked up on ingestion systems for Hadoop, and I was before that working at LinkedIn.
Hey, I'm Vinoth, and I'm currently at Uber building our real-time ingest pipelines into Hadoop. And then in the past, I worked on the key value store at LinkedIn called Waldemart. And then I've basically done data for a long time, stream processing, HPC, that kind of stuff.
So our agenda is quite simple. We just talk about what's data ingestion tool Sqoop used for. And we kind of decided to port this on Spark, basically run Sqoop jobs for ingestion on Apache Spark. And we'll explain why we did that. And spend some time on the details of how easy it was for us to implement that. And lastly, talk about some numbers between the MR versus the Spark and tell you guys where we are. So as simple as it seems, in the beginning, ingestion was basically between SQL to Hadoop, and Sqoop kind of solved that for a major part. You would ingest from MySQL, Postgres, and JDBC-like sources into Hadoop, which is HDFS and Hive. But over time, what's happened is, and usually if you look at companies like Uber, the ingestion needs have evolved. I know you kind of have sources which are not just JDBC-like. They're like non-SQL, NoSQL data stores you want to ingest from into Hadoop. Maybe Mongo or Cassandra. And then you also have messaging systems. And a company like Uber, we use like Kafka so heavily. There's a lot of pipelines where you want to get from Kafka to HDFS or from HDFS to Kafka. So some of these things are handled now with Sqoop. If you look at the Sqoop's latest code, it is a very generic any-to-any data transfer tool. So I can use this Sqoop today to do MySQL to Kafka, even like a file transfer and an FTP thing to a HDFS. Or if you have Kafka and then you want to put it into MemSQL for some reasoning, like without much transformations in between, you can do that. So that's Sqoop today. And I was kind of working on this. And if you want to understand how this is made possible, Sqoop actually has connectors. I don't think this should come as a surprise. If you want to make anything pluggable, you kind of give an API. So Sqoop similarly has connectors. There are tons at this point being written. There's one for Kafka. There's one for MySQL, Postgres. Even like legacy sources like Teradata and Netezza have connectors. So main thing about connectors are they express themselves through configs. So they're configurable. You kind of tell a connector how it can connect to its data source. For instance, a Kafka connector would tell like what's the Zookeeper port or the broker configs you need to use to connect to it. And also it has job configs. For instance, if you're writing data from HDFS to Kafka, you probably need to configure it and say which topic you're going to write data to. That, again, is simple stuff. Interesting thing about Sqoop that we looked at and why we wanted to port to Spark is it also has this APIs. Very importantly, how to partition data from a data source and how to extract data and load data. The reason why the extract and load makes sense is because a Kafka connector can support both writing into Kafka topics and reading from Kafka topics. So this is in general the connector API as it exists today. So why did we do Sqoop on Spark, right? Like currently, if you ask me this question, what it does or uses, it uses MapReduce engine or the MR APIs to do this transfer from source A to source B. And they use the MR engine to achieve the parallelism. That means if you're importing, say, millions of rows into Kafka topics, you basically kind of achieve the parallelism you want by running a MapReduce job. For us, Sqoop and Spark, I think the things are obvious here. Why? Because MapReduce is slow. There were a lot of use cases where you want to actually do the transformation, which currently wasn't supported. So you just do you partition, extract, and then load. But it's nice if you could do some transformation in between. And the MR API kind of makes it clunky, right? You just cannot have a changed set of operations in case of MapReduce. So good news is we looked at it as just as a hack thing, and the execution engine was very pluggable. So we ended up thinking, why not use Spark? Spark is like used, and why not just express our ETL as Spark jobs using Sqoop? It's obviously faster, and I don't think it's something I have to echo more than anybody here in the Spark Summit, that it's a lot of good community around it. So like, when I was doing this and people asked, so why not use the Spark data sources? Like Spark has evolved and there are data frames, and why not use it? Sure, you can. But I think when we started this, I don't think there was data frame APIs. It's a recent addition somewhere down in December. So you can surely use your data sources and do the ETL part. But if you were already running Sqoop jobs, you can switch from an MR to Spark with a simple config change, saying that the execution engine you want to use is Spark at this point of time, and that is where we want to leverage. A lot of stuff like incremental ingestion, reading only subset of rows and subset of data is possible in Sqoop, so you don't have to rewrite any of that logic in your new Spark job. So that's the reason we did it. So the next thing is, how do we do Sqoop jobs in Spark? It turns out it wasn't too hard for us to get this working at all. Sqoop has a bunch of APIs already to create jobs. So that is what we leverage. We didn't have to do much change. The two things that we really focused on was how do you do job submission now, and then how do you do job execution. The rest of the talk will just focus on these three things and end it with some of the insights we had. So creating a Sqoop job API, since this is a 15-minute talk, I really can't go into every detail of the code. It's a bunch of setup you do to kind of configure what is the from and the to. So if I have to explain, you have to kind of configure that. Say you're doing from MySQL to Kafka, what is the MySQL table you're going to read from, and what is the Kafka topic you're going to write to. You may also have to kind of create some configuration objects at that point of time, and that is how a Sqoop job basically is constructed. Once you do this, we just put the Sqoop job in the Spark context, and we execute that. And we'll go more into the details of execution in the later slides. Job submission was kind of the trickiest part to get it right, because the way it is currently done in Spark, there's not many clean APIs to do submission like MR client does. Even we were able to do submission, it's really hard to kind of get back job statistics. So we explored a few things. So what if you could just run the Spark inside the Sqoop server? Sqoop server. The only thing is it's in process, and you may not have a high availability. Second, we also explored using remote Spark context that Hive on Spark project used, but it was way too much for us. Lastly, we could just create Sqoop job as a driver program and use the Yarn programmatic API to submit it. And that's what we chose. And our APIs is basically, it leverages a lot of Sqoop, and you programmatically or you can directly submit these Sqoop jobs into Yarn client. It gives us a lot of flexibility because currently Sqoop did not have a good way to schedule these jobs periodically. So you can kind of do that with this with Uzi integration very easily. So you can convert an existing Sqoop MR job to run on a Spark with a simple config change and schedule it with Uzi. The rest of the slide will just go through a detail of what Spark job execution looks like now, and I'll hand it over to Vinoth.
Yeah, so this is kind of the under the hoods look into what actually happens when we execute a Sqoop job. So as we looked at this before, the job already defines an extract API and a load API, which defines how to extract the data from a source, and then load says how to write it into like a destination, right? So underneath, we first look at the job config and look at how much parallelism it needs. And we create a bunch of partition RDDs out of it. And we pretty much call a map on them so that we get like a parallel execution container for each such partition. And then we chain it, and that gives us like an extract RDD. And then which basically runs all the extractor logic and gets the data out and kind of stages it like how any normal Spark job would stage data between the stages. And then we call another map, which gives us a bunch of load RDDs, which is basically, again, context where we insert data into the destination and then collect basically, kicks off the entire DAG. So high level, it's like 3 steps. So you can see these RDDs that we do. So the thing is, all of this in the MapReduce part of it is, again, done by mappers and reducers. And that's the key kind of takeaway. And so another thing, right? So we have two stages, and that's kind of a little bit more thought through, because in most of these cases, you may not have one-to-one mapping between the number of extractors and the number of loaders. For example, you may have a lot more partitions on your MySQL sharded databases or a lot more tables, but HDFS only lets you write one writer per file at any given point in time. So we could, with Spark, since this is no longer a simple map and a reduce, and you can define arbitrary DAGs, we can actually put in like a repartition inside to kind of group records to make bigger files on HDFS and things like that. And yeah, so I guess we ran some micro benchmarks, and then unsurprisingly, Spark was pretty much always faster than MapReduce. And we saw in this graph, if you look at it, we kind of see an anomaly as we increase the number of extractors. Spark kind of goes up. It's actually, we traced it down to an actual anomaly in the data and how Sqoop actually partitions a table. So high level, the table had some primary key columns. And then since the strings weren't like splitting evenly across ranges, there were some straggler executors which were still running even as we increase more executors. But as you can see, to get the same amount of time, MapReduce still has to use like so much amount of executors. And then we tried a table with like more good partitioning and spread across the primary key columns. And again, like you can obviously, you're all here, so you guys know Spark is in general faster. So high level, at Uber, we care latency across all things. So for us, even in our ingest jobs, if we can stage the intermediate output from the extract and the load phase in memory before we load it into our destination, that's like a faster kind of load time for us. So that's the basic motivation behind this. So quickly, what was easy? So I think what we validated was the pluggability of the executors. We did not make any single change in the connector APIs to make Sqoop now run on Spark versus MR. And then general Spark love, testing Spark applications in Yarn and like standalone mode, and that is really good for iterating. And then as Veena mentioned earlier, since we did the Uber jar approach, we were also able to like schedule this via Uzi and then have it like periodically ingest stuff. And what was not easy, again, like lack of a very clean submit API. Maybe things will improve going forward. And then in Sqoop itself, most of the pain was around like making a bunch of these core classes as serializable so that Spark can move stuff around. And again, like so this project now became like a melting pot of Hadoop and Spark dependencies, which Spark has its own Hadoop dependencies. So that caused some general pain around building and stuff. But well, next steps. So yeah, with 1.4, I think there's some steps to improve the job submission, maybe explore things around that. And then finally, since we have like a POC sort of working, and then we can port over the jobs, we're planning on proposing some extensions to the Sqoop connector APIs, which may let us do, say, filtering or some transformations. And our code is there on the link. If you guys are interested in trying it out, just try it out. And yeah.